All right, so we were halfway-ish done. So let me ask you this. Had we gotten to the part on problem 4 where we were making our tables of values?
Yeah, we made our left table, we did like our right table.
Okay, so we made our xj of x table, but we haven't made our xj inverse of x table, right? Okay, so let's pick it up from there.
Now, some of those two pens you.
The what?
The pens.
Yeah, help yourself. So the x, and then we're going to do on the right side j inverse of this, like such. And so
I don't even remember. I want to be honest. Oh wait, no, it's just -3x.
So J, remember what I said, do not just take the points out of your first table and switch them to make, that's really defeating the purpose of all of this then, because of course then your graphs are going to be inverses because you cheap shotted it. What we want to do is we want to go in legit and find the actual values just to verify that the algebraic inverse that we think we found, which by the way is up here on the board again, that we want to make sure that what we found that we claim to be the inverse is actually the inverse. And if the points work, great. If they don't, then that'll send us backwards to say, where did things go wrong? So yeah, that's actually what we want to do for this particular tables. We want to pick, remember when doing log tables, it's harder, not harder. You just have to be more selective about which x's you choose. And recall when we did logs the other day, the numbers that we want this to be, I'll underline it in purple for you. We want that to be 1. We want it to be 2. We want it to be 4. We want it to be 8. Remember, because those are all easy to evaluate logs with a base of 2. I hope that's ringing some bells. So like, how could I make the purple thing equal 1?
-3.
If x were -3, that's a dandy of a choice. And then if I put -3 in, then I've got to evaluate this all out. And your work should start with this yellow box. You want to do the math in the yellow box. So if you put -3 in place of x, -3 plus 4 is 1. What's log base 2 of 1? It is 0. Good job. Good memory. Remember that any log base anything with an argument of 1 is always going to be 0, and 0 plus 2 is 2. And then it's nice to look over and see, yep, I had that point on the other table too. But I didn't just write it because I switched them. It happened naturally, which is a great sign. What's the next thing I want to make is I want to make the purple thing equal 2. What would that be? Yeah, -2. And if you put that in, -2 plus 4 is 2. What's log base 2 of 2? And 1 plus 2 is 3. And then you want to go look over there and you're like, yep, I see that point also. This is great news. Remember, they appeared in the other table. They just were backwards. And that's what we're hoping to see here. If I want to make the purple thing equal 4, then what's x? 0. What's log base 2 of 4? 2 plus 2 is 4. And then we're hoping that the point 4 zeros on the other table. And sure enough, there it is. And then there's one more really good one here. And then we should have enough to make a pretty good graph after this. 4 is what we need for the x, because that'll make 4 plus 4 equal 8. What's log base 2 of 8?
3.
And 3 plus 2 is... And there's 4, 5, the flip-flop of 5, 4. And I think just maybe to find one more, why don't we go ahead and make the purple thing? Well, it's not purple anymore, but let's make the argument of a log be 16. What would x have to be for that? 12. So if x is 12, 12 plus 4 is 16. What's log base 2 of 16? 4 plus 2 is 6. And so that should be enough to say, yeah, we're looking really good. The only ones that aren't there are the fractions, and those will take care of themselves as we go. Okay. So what we're going to do now is, I think, I had these in my notes the other day. I think I actually had this on here. Let me see. Yeah, I had it. There it is. Oh, that's the wrong assignment. You turkey. Oh, it's this one. Yeah, it's my guy there.
Do you want to see?
Do I want to what? I'm already recording. Yeah. You scared me though. So let's graph the table for J inverse of X. And those points again were, and we can plot either one first. It doesn't matter. I think let's do the green one first. So let's go back and plot j of x. Have you guys plotted j of x yet?
No.
Well, let's plot it together. So we have to go to the point 1, -3.5, which is down 1, 2, 3, and about a half. And then we're going to plot the point 2, -3. And then we're going to plot the point 3, -2. You can start to see the bend happening now. And then we're going to plot the point 4, 0. And then we had a couple more. We have 5, 4, and 6, 12. So 5, 4 is right 5 up 4. You can really see it's growing now. And then the last one is 6, 12. And 6, 12 is going to be a stretch, but we can just kind of improvise. It's just kind of good to have something to hold on to up there when you go to graph. So 6, and then there's 10, and that's probably about 11, and then go up again. That's probably about 12. I'm just guesstimating. So can you see where the asymptote will be for this particular graph? Is it a horizontal asymptote or a vertical? It's a horizontal. And you should, I hope, be able to make out that this red line right here is a horizontal asymptote. So in every graph will have either a log or an exponential curve. They're all going to have an asymptote. The exponentials have horizontal asymptotes. That's the plane coming in for a landing that we talked about. So this particular graph is going to look, so it's going to hug along this asymptote. There's 0 chance that this goes well. And then it's going to start to curve up like this. What's that? It's not a disaster yet. Oh, my wristband is catching on my board. God dang. Oh, that wasn't terrible. That's pretty bad. But anyways, there's the graph of j of x. And now, since we did all that hard work, let's go make a graph of j inverse of x, or what we claim to be j inverse of x. But it's a good sign when all the numbers are flipping like they're supposed to. So for this, I'm going to switch colors. I think I'll go to, I don't remember what I did on the other ones. I did green and red. So I'll do red for the second graph. So for the second graph, we just have to plot the points that we just worked so hard to find. So the first one was we did -3, 2. And then we did -2, 3. And then we did 0, 4. And then we did 4, 5. And then we did 12, 6. And again, there's a stretch out here to 12. I find it easier to go up to 6 and then go out and just try to improvise where you think 12 is going to be. Maybe like that, something like that. What kind of an asymptote does this curve have? A vertical one. Very good. So exponential curves have horizontal asymptotes. The plane comes in for a landing horizontally. Logarithmic curves have vertical asymptotes, and I'll draw that one for you as well. So this thin red line going vertically is another asymptote. So the two straight red lines that you see on this graph are the asymptotes that the graphs come up against, so to speak. So anyways, this graph should hug the asymptote like this. And then it starts to break free, break away. And then it heads upstairs like this. Ooh, that one went really well. Look at me. Bam. So what is our goal here? What's the last thing we have to do? There you go. So we're going to graph the line y equals x. And the line y equals x is just the perfect line from algebra 1 with a slope of 1 that goes through the origin. And the goal here is that, this is a big, big task. We're trying not only to show that the graphs are inverses, which is actually really cool, but we're also showing algebraically. So this is everything kind of in one package. Are you ready for problem 2? So problem 2 was the one that I skipped on Thursday, and the reason I skipped it is because of the domain restriction that we have to do. So let's begin with this. Let's find the inverse. So for step 1 of finding the inverse, we are going to switch the letters. So we're going to have x equals the square root of y plus 2. And then what do we do? Square both sides. So we wind up with x squared equals y plus 2. And after that,
Y equals X squared.
Right. So we can say that G inverse of X is equal to X squared minus 2. So for color coding purposes, for when we graph here in a few minutes, I'll be consistent. The one I'm circling in green is our OG function. And then the one I'm circling in red is what we claim to be the inverse. And our goal will be when we graph those that they look to be perfect mirror reflections about that line called y equals x. So depending these ones I can kind of go both ways on, but depending on your level of comfort. So would any of you know how just to graph the g of x function just without doing a table? You do, you just may not remember that you do. So let's do it the way we've been doing it to be consistent. By the way, it's just a square root function shifted 2 units to the left, FYI. But let's go through the motions and let's make the table. So let's do a table for x and g of x. So what's a good first x to pick? Two's fine. Yeah, there's a few others, but 2 works for me. Because if you put in 2, what's 2 plus 2? And what's the square root of 4? So 2 is a point on this graph, but we need a ton more than that. How about, what if I picked -2? Can I do that?
No.
Sure you can. What's -2 plus 2?
0.
What's the square root of 0? That works just fine. Normally, a negative number would break the domain of a square root function, but if it gets offset by something that unnegatives it, if that's a word, then it's fine. How about -1? What's -1 plus 2? What's the square root of 1? Okay, now we're going to head in the direction that Brady started us off on in the first place. What's the next number after 4 that's square rootable? 9. What do I need x to be to make a 9? 7 is a good x, because if you put it up here in that little purple egg, 7 plus 2 is 9. So if I pick 7, 7 plus 2 is 9. The square root of 9 is 3. And we're going to run out now because what's the next number after 9? And I don't want to try to go far enough out to 14. That's way outside. So you can if you want to, but this will probably be enough. All right, let's flip it now and let's make a table for x and g inverse of x. So now we're focusing on the function that's in the red bubble. And this is where, for the first time, you're going to see a domain restriction. You're going to see here in about 5 minutes why I saved this one for last, okay? So for the record, I can do a whole bunch of numbers on this one. I could do like -3, -2, -1, 0, 1, 2, and 3. Those are all reasonable numbers to put into the G inverse function because they're all within a comfort, like a zone, like a radius, if you will. So what's -3 squared? 9 minus 2?
7.
7. What's -2 squared? 4 minus 2 is 2. I feel some silence. I hope everyone's clear that we're plugging our x's right in there, right? We're in the red function, the inverse function now. Put in -1. What's -1 squared? 1 minus 2. -1. Put in a 0. What's 0 squared? 0 minus 2. 1 squared. 1 minus 2. 2 squared. 4 minus 2. 3 squared. 9 minus 2 is 7. So I know I kind of ran myself out of real estate there, but those are the numbers that are going to work for our inverse function. So let's go through and first let's plot g of x. That was the first one where we only had 4 numbers in the table, 4 points in the table. So I will use green dots for this function. And if you're stuck on graphing points, then just let me know. But there's 2, 2, and there's -2, 0, -1, 1, and 7, 3. So you've seen this graph before. You know what a square root graph does. And it behaves like that. Still good? Okay. Now what I want you to do is graph the G inverse function. And there are 7 points there. I mean, obviously there's more than 7. I chose the ones that would fit reasonably on the grid. So I'm going to switch colors here to red dots. And we're going to graph all those points. -3, 7, -2, 2, -1, -1, 0, -2, -1, 2, 2, and 3, 7. Yeah, what the something, huh? This is the first time where we kind of go, wait a second, this doesn't work, does it? I think it's pretty obvious that the red graph is not going to be a mirror reflection of the green graph. And there's a reason for this, and I'll show you what that is. What we're going to have to do is something called a domain restriction. And assuming you've done every assignment in this class, like I teach based on assumptions. And one of those assumptions is always that you've completed the work that was before what we're doing now. I gave you guys a worksheet a couple of weeks ago, probably on domain and range. And also on that same worksheet was the question of, is this a function? Remember this? There were like a ton of them. Is it a function? Yes or no? And state the domain and state the range. So here's the problem, and I don't think you should write this part down because you're just going to have to do some erasing. But currently, the red graph goes like this. And if you were to draw this, if you already have it graphed, it's no big deal. Like, don't sweat it. But this is the line y equals x. And I think we're all bright enough people here. We can agree that the red and the green graphs are not inverses of each other, correct? And the reason why is because too much of the red graph has been allowed to survive. What I want you to picture is this right now. I've never asked you to do something called the horizontal line test before, but picture right now the red graph falling over on its side. Well, first off, let me ask you this. In its current state, is the red graph a function? Of course it is. It passes the vertical line test, doesn't it? We agree that the red graph, the quadratic, is a function, but if it were to fall on its side, would it still be a function? No. And so what we have to do to make this legal and legit is we have to essentially cut half of the red function off. You can kind of picture like as if you had a big pair of imaginary mathematical scissors. And just imagine, if you will, that you went right here to where this arrow is pointing, right there. And you cut right there, snip, and you threw half the graph away. If after you did that, if the red graph then fell on its side, would it still be a function? Yes. What that is that's called a domain restriction. What we do a lot of times is we take a function that is a function, but we think ahead about what its inverse would look like. And the trouble is, if his inverse, by the way, if you haven't figured this out, when a graph inverts, it really essentially just falls over. Like there's a little more to it, but it really is just like, boop, it topples, right? And if you think about the function and say, what would make you not be a function if you fell over? Or like, how could I fix that? Then we can do a restriction on the domain. So what we're going to do, and this is a free-for-all, by the way, you can pick either or, and I'll show you this in a second. If I were to eliminate everything on the red graph to the left of the vertex, are the red graph and the green graph now inverses? Mm-hmm. They are. And the reason they're able to be inverses is because they're both functions. That put a restriction on one to make it match the other, his homie. by the way, you also could have the question I would have asked, and I probably did ask. I mean, I'd like to think that I did when I was your age and I was first learning this is, well, how did you know to eliminate that side of the graph? And the answer is, it doesn't really actually matter. There's still going to be inverses of each other, regardless of which half of it you kill. Like this. Which that does not look correct to me. So I think in this case, did I do something silly? Are those inverses of each other? I don't think so either. So maybe it does matter. So let's go back and let's restrict the other one. Oh, you know what it is? We have to kill the negative side. There's a conversation here which we don't have to have. But this is God bless you. This is a positive graph because it's the positive side of this. It goes up, not down. And that's why we need to unalive the negative side of the red graph. So to keep them inverses, of course, we have to keep the positive. So we have to.
Yeah, that's the one with the possible.
Correct. And so like if the green graph, I'm going to sketch something and it's going to be purely a hypothetical. I don't have a lot of colors left, but let's say that this is the graph that we had. And it went down. Like this. Oh God. Oh, good God, that got away from me in a hurry. Oh, I'm so sorry you had to see that. You need eye bleach after that. So if our graph had been the negative version of the square root graph, then do you see now that by unaliving the positive side of this graph, once again, we get inverses.
Yes.
So anyhow, that's what I avoided on Thursday was the domain restriction. So in order to do a domain restriction, what it looks like is this. So on the test, it'll say restrict the domain. So we take the function named g inverse of x. And then after this, you guys can work. Sorry, this always takes longer than I think it should. So for this function, we restrict its domain to say the set of all x's such that x is greater than or equal to 0. So you should probably write that down. I'm going to write that down again for you. I'm going to write it over here so there's not so much chaos on the board. We restricted the domain to say the set of, that's a curly bracket, all x's such that, that vertical bar in mathematics is shorthand for such that. So restricting it to the set of all x's such that x is greater than or equal to. And again, the reason I chose the number that I chose is because the vertex is right here. Nice color there, genius. The vertex is on this line and that has a name of 0. That has an x value of 0. So we just restrict the domain to the right side. And that is that. Okay. That's confusing. I'm assuming that's confusing. But again, why did we have to restrict the domain?
Oh.
I don't know. I just did it because you told me to. There were a couple of reasons. Number one, we restrict the domain so that when it fell on its side, it would be a function, but we also did it specifically so that it would match when it fell on its side, the inverse of the green. So we're doing that for sort of 2 reasons there. So I do have assignment 19 for you. I'm going to hand it out. I'm not expecting you to get it done. We'll work on this today. We'll also work on it tomorrow. I will be gone. I'll just keep this recording going. Not that anybody cares, but I'll be gone Thursday for a dental appointment. You guys, I'll remind you of this throughout the week. You guys have to go to the library on Thursday. The person that is subbing for me on Thursday has got another engagement that they have to go to. So I've already cleared it with the librarian and the office, and they know that you guys will just go to not this room 5th hour, but just go to the library and do whatever work we're doing that day. Got it? Cool. All right. Let me get you your assignments.